Hello everybody. Today I am interacting with you on this course vibration of continuous system. So far we have completed 5 modules and 6 modules. Sixth module is currently going. So I will tell you about the. I will summarize what is done actually in each module, and then I will answer the questions raised by the learners in discussion forum. After that, I will answer the questions that was asked for the live sessions. So let me share the slides in which the summary of the modules completed will be available. Okay. So here I will share this slide. So this is interactive session 1, and in this interactive session, I will highlight the topics that was covered in module 1, 2, 3, 4, and 5. Ongoing module 6, I will not touch today. In the next live session, I will discuss about the module 6. So, clarification of doubts raised by the discussion forum learners in the discussion forum is important consideration of that this interactive session, and I want to answer the questions that was received from the learners for the first live session. In the discussion forum, some questions were raised, and I answered these questions with the help of text through email. Now we'll discuss with the help of equation, because some doubts have to be cleared by writing equations. Then clarification of other doubts or any new question that you can ask in this interactive session will be answered. Okay. So let me discuss what I have done. In module 1, I have discussed the discrete and continuous system in brief. That is, what is discrete model and what is continuous model. So two types of model that are possible in dynamic analysis was introduced to you. And then I discussed the modeling of undamped and damped vibration system. Because in dynamic analysis, there are mainly 3 elements: the inertia elements, then stiffness element, and this damping. So this damped vibration and undamped vibrations were discussed in this module 1 with the help of equations. Then general approach for time domain analysis of any arbitrary excitation that may act on the system was discussed. Then there is another very important tool, powerful tool that is used in vibration analysis, that is called transform techniques. That means original equation of motion was transformed into other domains. Equation of motion generally is found in the time domain. However, with the help of some transformations, this is transformed into some other domain. For example, the Laplace transform, the equation of time domain is transferred to the Laplace domain S. And then another type of transformation that is called Fourier transformation, that is used to transform the time domain equation to the Fourier domain or frequency domain. Okay. So discrete model, the physical parameters of the system are lumped at the some point, and generally the mass, the gravity, the was effect of gravity, that is the mass or weight, was lumped at the center of gravity. This is centroid of mass. And discrete models are characterized by finite number of degrees of freedom because we are lumping the mass at different locations, and any system or any particle we know that can exhibit three motions in XY direction, XY and Z direction. So each mass is considered as a particle in the discrete model, and then we can determine the degrees of freedom, which is a finite number. But in continuous model, the mass has a distribution, that is it is a distributed parameter, mass and stiffness, and therefore the degrees of freedom are not finite, that is infinite in continuous system. The most important feature of the discrete model is that it is described by ordinary differential equations, whereas in continuous model it is described by partial differential equation. You can see this example, that is a cantilever beam in which the mass and stiffness is distributed along the length of the beam. So it has distributed mass and the model is continuous model. So equation of motion, this type of structure will be governed by a partial differential equation. However, here you can see that if the mass of the cantilever is assumed to be lumped at the free end, and then the elastic properties of this beam, that is modeled as a spring with a constant given here, is attached to the mass, then it represents a idealized discrete model of single degree freedom. So that is the difference. One can idealize the continuous model into a discrete model, but the most practical aspect is that in any model, the distribution of the mass and stiffness are continuous. That means it is throughout the domain of the structures. Okay. So we discussed two aspects of vibration. That is the free vibration of underdamped system and forced vibration. We have selected the underdamped system because in underdamped system, the motion is oscillatory. In other cases of damping, that is overdamping system or critical damping system, the motion is not oscillatory, it decays with time. So underdamped system is characterized by this parameter C by 2m whole square is less than K by m, where C is the damping constant. Here a dashpot is represented representing the damping of this model, and m is the mass of this model, and K is the spring constant. Here the external force Ft is acting. The response quantities are displacement, velocity, and acceleration. The velocity and accelerations are time derivative of this displacement. That is, first derivative with respect to time of the displacement will give you the velocity, and second derivative of the displacement with respect to time will give you the acceleration. So for such system, the response in absence of this force, that is the free vibration, is given by xt equal to e to the power minus xi omega nt into a cos omega dt plus b sin omega dt. So here a and b are constants of integration, and omega d is damped natural frequency, and it is given by omega n root over 1 minus xi square, where xi is the damping ratio. That is the ratio of the actual damping to the critical damping. Omega n is the undamped natural frequency. It is nothing but root over K by n. So these quantities, that omega n, xi, are important properties of this system, and therefore we we can relate this with this damping, this C, that is we discussed earlier, that is omega D is the damped natural frequency, which is actually less than the undamped natural frequency, because it is given by omega n root over 1 minus xi square. So naturally, if xi is less than 1, then this quantity omega d will be less than omega n. However, in actual situation, xi is very less. Say it ranges between say 1% to 5% maximum for structural material that we use in our engineering applications. And even it may be less than 1 also in some cases. So in that case, the omega d is approximately omega n. So you can see the nature of the solution, that the response, that is the displacement, or even if you find the velocity after taking the time derivative, it will contain a decaying term that is exponential to the power xi minus xi omega nt. Because of negative exponential, it will have a decaying tendency with time. Although it is oscillatory, but it will decay and ultimately come to rest. So this is the property of the damping. All physical system in real situation contains damping. Whether you model it as a damped structure or undamped structure, it does not matter. But ultimately, in actually, when the system is subjected to excitation and the excitation is withdrawn or excitation ceases to act, then with time the motion will decrease and the system will come to rest. Say sudden earthquake comes, so the structure will be subjected to rigorous motion for certain time when the disturbance acts, and as soon as the disturbance ceases, then gradually the system comes to rest. This is due to property of damping. Okay. Now, the initial condition is the most important parameters in the vibration analysis. If the system has some initial displacement or it is having an initial motion, that is having displaced velocity, then the motion is governed by these two parameters. So in terms of initial displacement, u is the initial displacement and v is the initial velocity, then the response quantity can be written after finding the constant a and b in terms of u and v. So earlier we have found that it contains a and b, two parameters which are unknown. And after applying the initial condition, we get the constants a and b. So now the response become xt equal to e to the power minus xi omega nt u cos omega dt plus v plus xi omega n u divided by omega d sine omega dt. So this is the expression for free vibration of single degree freedom system. And this expression can also be used in the continuous system when we discretize the equation of motion into independent equation of motion, just like a single degree freedom system, due to this model superposition technique and by virtue of orthogonality condition. So here you can see that oscillatory behavior of the motion, but it is gradually decreasing and it is coming to rest. So this part I have discussed, and this formula I have used in several occasions to solve the problem. You have got in assignment as well as also in other chapters. This formula is used to find out the other expressions. Okay. So now, if the forcing part is present, that means the system is subjected to forced excitation. That is now excitation in the form of harmonic function. then we can find that for linear system, the response is also harmonic. So in that case, solving two parts of the system, one with homogeneous part, that is, if I consider the right hand side 0, then I get the homogeneous solution just like free vibration solution. And considering this forcing part, we get the particular integral. So two parts are superimposed because as the system is linear. So after superimposition, we get this equation, that is the full solution. So this you can see, this is the homogeneous solution. The first part is homogeneous solution. This is coming due to initial conditions. But here, initial condition cannot be determined in isolation with only the homogeneous part. You have to combine this with the particular integral. And this part is particular integral, where delta st is the static displacement that can be determined as, suppose F is the amplitude of the force, then K is the stiffness. So F by K is the static displacement that you can take. Small r is the frequency ratio. That is the ratio of driving frequency to the natural frequency of the system. And phi is the phase angle. Omega is the driving frequency of the system. You can see here the response that first it will have a very irregular pattern. That means here you cannot see a regular wave because the transient part is influenced by initial condition as well as your this natural frequency, and damping actually limits the magnitude here, because if the system is suddenly starting the vibration, the magnitude will be high, but because of damping, the magnitude is driving frequency is equal to the natural frequency of the system. Then the amplitude of motion becomes infinite theoretically if damping is not present. However, due to presence of damping, the magnitude is limited. So that is the most important role of damping, that limits the magnitude of the vibration in the resonance condition, as well as also it limits the magnitude in the tangent part also, because if the damping value is small, the transient part will exist for a long time. And then steady state condition will start. So this is the steady state condition. And steady state condition will go on as long as force is acting. But this irregular part that you are seeing, I named it as a transient part, will be vanishing depending on the amount of damping. If damping is small, it takes long time to vanish. And if damping is high, it will damping very early. It will vanish very early. So steady state part depends mainly on the amplitude of the force and driving frequency. But damping has very limiting role on this steady state part. Whereas in the resonance, damping plays an important part. Now you can see one thing, that what is the resonance frequency for a damped system. Resonance frequency for a damped system is not exactly equal to the natural frequency. That is, driving frequency is not equal to the natural frequency in case of damped system. It will be slightly less than the this natural frequency, because the equation that you have seen, that for damped system the magnitude of this frequency, that that is the frequency where resonance takes place, is equal to omega n root over 1 minus 2 xi square. So here xi is the damping ratio. So you can see this. This is because of damping. But for undamped system, omega is equal to omega n at resonance. At resonance. Okay. In damped system, it is not so. So that aspect I have defined, and frequency response curve also I have shown you in this module. That is, the nature of the frequency response curve is that it is like increasing and then it is decreasing. It attains a peak value at the resonance frequency or very near to the resonance frequency. Now in the module 2, I discussed formulation of the problem by Newton's law, then Hamilton principle, Lagrange's equation. Newton's law is actually this force balance, and you can know in dynamic condition this the resultant force, the summation of force is external force is equal to mass into acceleration. So in this 3D cases, we have the resultant force in x direction, this summation fx, in y direction, summation fy, like that. And this is the acceleration of the center of gravity of the mass in x, y, and z direction. So therefore, we get this. After equating this, we get the force in the different direction or acceleration in the different direction. So in this way, we can formulate the equation of motion for the continuous system or a discrete system using Newton's second law. Then we have discussed the Hamilton principle, which required the knowledge of energy. That is kinetic energy. Because the body is in motion, we require to determine the kinetic energy. So kinetic energy for a system of particles is determined as half summation mj u dot j square. U dot j is the velocity. Okay. Now u dot j is the physical coordinate. Sometimes the transformation is required from physical coordinate to generalized coordinate via some transformation matrix. So in that case, the transformation matrix elements that you are seeing here, C is the transformation matrix. It contains the derivative of this coordinate, physical coordinate, with respect to the generalized coordinate. So sometimes this uj becomes a nonlinear function of this qk. So in that case, this transformation matrix contains some term which is dependent on qk. So that condition renders the kinetic energy to be dependent on the velocity as well as the generalized coordinate, that is displacement. So this situation is observed in some problems that I illustrated in video, just like a spring pendulum, which is of 2 degree of freedom system. And there we have seen that kinetic energy contains both the generalized coordinate and its derivative. Okay. Then we discuss the Hamilton principle, because Hamilton principle depends on the variation of kinetic energy and this potential energy. Potential energy can be written as the negative of the work done, and we can write this delta T minus delta P. And it is a integral formulation, that is variation of kinetic energy and potential energy is integrated with respect to time between the limits T1 to T2. So if we follow this principle, then it is possible to arrive at the differential equation of motion as well as boundary conditions simultaneously. This quantity T minus V is known as Lagrangian. So Hamilton principle for conservative system where non-conservative forces are absent, like damping and other applied forces, external disturbance are absent. Then we can write in a compact form that Hamilton principle is variation of Lagrangian, uh, variation L dt limit t1 to t2 equal to 0. That is the integration of the Lagrangian. Then for system where conservative forces are applied, that is damping is present in the model or external disturbance are also present. So in that case, Hamilton equation is written as variation of T minus B plus WNC. So this is the new addition. So WNC is actually the work done by the non-conservative forces and its variation is also taken. So this is extended Hamilton principle where you can include the damping as well as the external disturbance. Then we have Lagrange's equation, which is particularly useful for the system where we convert the system into a generalized with the generalized coordinate. We specify the system with the help of generalized coordinates. So this equation, Lagrange's equations, directly cannot be used for this continuous system, whereas Hamilton principle is applicable for continuous as well as discrete system. Lagrange's equation is applicable for in the discrete form. Even in the continuous system, when we use the technique separation of variable that you have heard in my video, after converting the partial differential equation into ordinary differential equation by means of separation of variable in time domain, then we have the equation in the generalized coordinate. So if the response is written in terms of space function into a time function, then on the basis of time function, the Lagrange's equation can be applied. So Lagrange's equation, again, it is not an integral equation, but it is a differential equation that you are directly getting. But you should not confuse that Hamilton principle is an integral equation. That means it does not lead you to lead to a differential equation of motion. It ultimately leads to a differential equation of motion when integral is completed. Integration is completed. Here, this Lagrange's equation is in the derivative form. That means if I know the kinetic energy of the system in terms of generalized coordinates and its derivative, then I can write that d by dt del t by del q dot I is the ith generalized coordinate minus del t by del qi plus del v by del qi, where qi is the generalized coordinate. Here qi dot is the time derivative of the generalized coordinate, that is velocity with respect to generalized coordinate. So you can see here I have written minus dt by del t by del qi. But in most of the cases, especially for linear system, this term is 0. A nonlinear system or a system where the transformation of coordinate has been done and this transformation matrix contains these nonlinear terms, then this kinetic energy may contain these QIs. So in that case, that derivative is non-zero. Okay. In the module 3, I have discussed the wave equation and its solution, and then transverse vibration of string. So wave equation is a very famous equation, and it is found in this form: del square y by del x square equal to c square into del square y by del t square, where c is the wave velocity, that is equal to root over s by l. S is the tension in the string. That is, wave equation is determined with a model of transverse vibration of string. Now, for solving this type of equation, we require boundary condition as well as initial conditions. So two initial conditions are required because in dynamic problem, mostly it is in continuous system. It may be a second order equation or it may be a fourth order equation. Fourth order equation is obtained in case of beam, plates, membrane. And second order equation is obtained in vibration of transverse vibration of string, then axial vibration of bar and torsional vibration of shaft. So in the second order system, we require two boundary conditions. And two initial conditions are always true because whether it is in the fourth order or second order system, but in time coordinate, the equation is always second order system. So therefore, two initial conditions are necessary. The initial conditions are displacement and velocity at t is equal to 0 or the initial time in which the quantities are given. Okay. So wave equation in one dimension have been obtained in this form: yxt equal to gx minus ct plus fx plus ct, where c is the wave velocity. So this represents the two waves, that is the initial disturbance of the string. The string was in the form of in this configuration initially at t is equal to 0, and when it is released, the two waves are formed. One wave is traveling towards right and another wave is traveling towards left. And velocity of propagation is same whether it is traveling towards right or traveling towards left. So c is the wave velocity, and you can see this function represents the wave that is traveling towards right, and this function represents the wave that is traveling towards left. And it is traveling, and ultimately at the boundaries, it it struck, and then it is reflected from the boundary. Again, it will follow the same path. So this phenomenon is going on, and this vibration of the string takes place. Okay. So D'Alembert has given the solution of the wave equation in the form of initial configuration. So suppose the initial configuration that I have shown you, it is known as a function of x. Then D'Alembert have shown that displacement of the string at any instant of time can be written as half phi x minus ct plus half phi x plus ct. So this is the function. It may be a parabolic function. It may be a triangle, that is a linear function. So instead of this x, we now substitute x minus ct. Then it will represent a wave. Of course, a parameter half is associated. It will represent a wave traveling towards right, and half phi x plus ct will represent a wave traveling towards left. Okay. So transverse vibration technique is this model superposition technique. We assume displacement like that, a space function multiplied by a time function. This is called the mode shape function, and this is the generalized coordinate. And then we arrive at the eigenvalue problem. Because it is a second order differential equation, partial differential equation, we get the solution with two constants of integration. And after imposing the boundary condition, two boundary condition, we get the eigen solution. That means natural frequency and the mode shape. Okay. The model superposition technique that is now used to find out the response of the string, that is summation of mode shape function at a particular mode into the generalized coordinate in that particular mode. And then we can sum up to infinite number of modes, because in the continuous system, infinite number of modes are possible. So we get a equation like that. You can see after model superposition technique and orthogonality conditions applied to the differential equation of motion, one can find the discretized equation of motion or decoupled equation of motion. So here QIT represents the generalized force, which is the integration of fxt into phi x dx. Okay. So in the module 4, we discussed the axial vibration and torsional vibration of bar. And this type of vibration represents the same function that we used in case of transverse vibration of string. Because this is also a second order equation. You can see this is also second order equation. But here I have written the forcing term fxt, and it is the disturbing torque that I have written. So axial vibration of bar, this parameter AE is the axial stiffness, that is most important parameter here, and M is the mass per unit length, and here C is the damping per unit length. Torsional vibration Gj is the torsional constant, Ix is the moment mass polar moment of inertia, and C prime is the damping per unit length. So we use the similar technique, solve boundary value problem and initial value problem. Boundary value problem is solved to find out the natural frequencies and mode shape. After that, we can apply the orthogonality condition and this model superposition technique to get the discretized form of the equation in time domain. Then we get an initial value problem that can be solved in a similar way, but with the complete solution, not that initial value problem will be solved only for free vibration. That is not. You will find out the complete solution, homogeneous solution plus particular integral, then apply the initial condition. In the fifth module, transverse vibration of beam is discussed, and the 4 types of beam model are given in this video: Euler-Bernoulli beam model, Rayleigh's beam model, shear model, Timoshenko beam model. Beam models are considered primarily under bending. So here transverse displacement is the most important response quantity in all the models that you are seeing here. And bending moment is also present in all the models. But in some models, say, we neglect other effect, that is shear deformation and rotary inertia are neglected in Euler-Bernoulli beam model. Similarly, Rayleigh's model, the shear deformation is neglected. However, rotary inertia is considered. In shear beam model, we consider bending moment, shear deformation, but rotary inertia neglected. Timoshenko beam model, we consider bending moment, shear deformation, and rotary inertia. Timoshenko beam model is generally applicable for thick beam. That means if the depth to span ratio is greater than 0.1, then Timoshenko beam model will give a satisfactory result. Whereas Euler-Bernoulli beam model is applicable for the beam in which depth span ratio is less than 0.1. That is, it is a beam model where the other effects, shear and rotary. Shear effect is more predominant in case of deep beam. So therefore, Timoshenko beam is appropriate to model the shear deformation along with bending and rotary inertia. So the salient feature of this module is that the beam vibration equation is a 4th order differential equation. You can see here. Okay, so that equation is solved again using the model superposition technique. Of course, the boundary conditions here, 4 boundary conditions are required, 2 at each end of the beam. And you can see this hinged end, fixed end, free end, and sliding end are may be present in case of this boundaries. So we apply the boundary condition to get the eigenvalues and natural frequency. So this is the eigenfunctions of the beam. And A1, A2, A3, A4 are constants of integration that can be determined by imposing the boundary conditions. Boundary conditions that I discussed, these are classical boundary conditions. But there are some non-classical boundary conditions. Suppose, for example, at the end of the free end of the beam, say it is a cantilever, the concentrated mass is acting, then it becomes a non-classical boundary condition. Again, if the free end of the beam is attached with a spring, linear spring or rotational spring, then it becomes a non-classical boundary condition. So that type of boundary conditions also we met in practice, and I have given in this module the solution technique and the important results for such type of boundaries. So we have discussed this classical boundaries: simply supported, cantilever, free, and fixed beam. Then orthogonality condition of the modes, which are same in all cases of continuous system that we have discussed earlier, also exist in case of beam model, and we have applied this to discretize the equation of motion. So this is the free vibration equation that we obtain ultimately, and one problem I have demonstrated in this video with this help of this equation. So AI and BI are constants of integration that should be found by applying the initial conditions. And you can sum up to some finite number of modes. Generally, first few modes are sufficient for finding the displacement accurately. However, more number of modes are required to find out the bending moment and shear force accurately. Okay. So let us discuss the questions for the live session that I received. The amplitude of free vibration. One question was that how the amplitude of free vibration can be represented in terms of initial condition. So free vibration equation is written in this form. I here, for simplicity, I neglected damping, but with damping also same procedure can be adopted. So xt is written as u cos omega nt plus v by omega n sin omega nt, where v is the initial velocity, u is the initial displacement. So this can be written by using this technique that root over divide right hand side by this quantity root over u square plus v by omega n square and multiply this with the same quantity so that equality remains. So then we can express this xt as a cos omega nt plus phi, where a is the amplitude of the free vibration, and that is nothing but root over u square plus v by omega n whole square. So in this way, one can express the amplitude of free vibration in terms of initial disturbance, that is initial velocity and initial displacement. And tan phi, of course, the phase angle can be determined from this relation, u omega n divided by v. Second question was there, how the damping is taken in Lagrange's equation. Lagrange's equation that I discussed, the right hand side was qj, that is the generalized force at the jth coordinate. Now generalized force contains this, if it is a non-conservative system, then it contains the damping force as well as this applied disturbance. So here we can take this as a damping force. It is damping force, you know, that damping constant into velocity if we consider the viscous model. And since the damping, the velocity is opposite to the motion, damping force is always opposite to the motion. Therefore, the force is written with a negative sign. Now, alternatively, the damping can also be taken by this function. There is a release dissipating function R equal to half Cj into Q dot J square, where Q dot J is the velocity. So it can be also taken like that. This, instead of taking the damping force in the right hand side, we can take the first derivative of release dissipation function with respect to velocity. So in that case, the damping will appear in the equation of motion. Then another question is, how is damping determined experimentally? So there are two methods for determining the damping. One is logarithmic decrement and another is half power point method. In logarithmic decrement, we record the time history of decaying motion, and then we find this parameter, which is logarithmic decrement. And suppose we measure the amplitude at this instant, say x1, and after jth cycle, we measure another amplitude xj plus 1. Then we can find the logarithmic decrement as delta equal to 1 by j, natural logarithm, x1 divided by xj plus 1. Now, this delta can be related to the damping ratio chi with a simple relation delta equal to 2 pi j. And this is value for small damping. Usually damping is very small in practical situation. So therefore this equation can be safely applied. So from this equation, chi, the damping ratio can be determined. So that is one method. Then another method is half power point method. So in this case, the frequency response curve has to be obtained. So suppose in the experiment, this curve is obtained. That is the variation of amplitude with the variation of driving frequency that is obtained. Or after obtaining the time history, we can perform the Fourier transform and we can get the frequency response curve. Now from the frequency response curve, we can note that the Q is the point where maximum displacement occurs. So this is denoted by X max. So we select another 2 points, P1 and P2, which are called half power point. And these points are at 0.707 X max. So corresponding to these 2 points, we note this frequency omega 1 and omega 2. And difference of omega 2, omega 1 is del omega 1. This is the bandwidth. If the damping is small, then bandwidth will be very small. It will be a very sharp peak. But if damping is large, the bandwidth will be large. So you can see that this 0.707, why the 0.707 X max is selected? Because it is nothing but X max by root 2. And if I square this 0.707 X max square, that is square of the amplitude is related to the energy. So you can say that it is the half quantity factor is coming. If 0.707 is squared, then we'll get 0.5. So in that case, we get the half of the square of the amplitude if we square it. So therefore, this point is known as half power point. And by this half power point, we can determine this damping. And you can see damping is related to the bandwidth and natural frequency of the system. So damping ratio is equal to delta omega divided by 2 omega n. So omega n is found corresponding to this peak. So this is the omega n, and this bandwidth is found corresponding to these 2 points, and then damping is determined. Okay. Next question is, how initial conditions affect the wave propagation? That I have discussed in my earlier slide, that D'Alemberts have given the solution of the wave equation in this form: y is equal to xt equal to g of x minus ct plus f of x plus ct. So if the initial configuration of the string is defined by a function phi x, then the solution is written as half phi x minus ct plus half phi x plus ct. So this represents the solution in terms of initial conditions. Then other questions raised in the discussion forum that I have replied through email, but here I will discuss with the equations. So one question was that regarding the degrees of freedom of double pendulum. So equation for determining the degrees of freedom for system of particles is written in video is small n equal to 3 capital N minus C, where capital N is the number of particles and N is the degree of freedom, C is the constraint equation. Number 3 is assigned here because it may represent the motion in 3D space. So a particle is allowed to move in x, y, z direction. So therefore, the number 3 is assigned. So therefore, if I apply this equation and constant equation for this pendulum from these parameters are this x1 square plus y1 square equal to L1 square. And another equation is x2 minus x1 square plus y2 minus y1 square equal to L2 square. Other additional equation that have to be brought because the double pendulum is in this xy plane. So there is no motion in the z direction. So it is in the plane of this paper or slide. So therefore z1 equal to 0 and z2 equal to 0. So these two additional equations are also added here, and therefore we get number of constant equation 4. So if n is 2, then 3 into 2, 6 minus 4 equal to 2. That is the degrees of freedom of this system, double pendulum. So 2 degrees of freedom. Also, if you want to retain these two constant equation, then instead of 3, you can use small n equal to 2n minus c to represent the motion restricted only in the xy plane. Okay. Then another equation was there, the regarding the application of Lagrange's equation for this problem. Here you can see the kinetic energy is found out, the kinetic energy of this mass plus kinetic energy of this mass capital M and kinetic energy of this pendulum mass small m. So you can see here the resultant velocity is considered to find out the kinetic energy, and due to this resolution of vectors we get this resultant velocity square as x dot square plus L square theta dot square plus 2 x dot L theta dot cos theta. Now cos theta term is containing the generalized coordinate theta because Q2 is theta. So therefore in this problem the generalized coordinate is coming. Hence the partial derivative of the kinetic energy with respect to Q2 is not 0 because cos theta is appearing here. But if we assume the displacement and rotations are small, then cos theta is approximately 1. So in that case, the kinetic energy becomes again the function of only the derivative of the displacement, that is the velocity. So that equation del T by del Q2 is 0 in case of small displacement. But if you do not assume small displacement, then you have to differentiate with respect to theta also here. Okay. So that is discussed in this video, and this clarification was given in this email also. So because of this initial assumption of small theta, this cos theta can be taken as 1, and therefore del T by del Q2 can be taken as 0. Then another question in the discussion forum was this: if rho is the mass per unit length integrated over length dx, and why it is called mass normalization? Because due to in the process of integration, you can see that mn equal to integration rho phi n square dx, and if I normalize the mode shape function as this quantity, root 2 by rho L, then we can get this generalized mass equal to 1. So we have taken the normalization constant of the mode shape A in such a way that generalized mass becomes 1. So therefore, it is called mass normalization, but it is understood as a normalization of mode shape with respect to mass. Then regarding the integral to find out the generalized force. Generalized force for the discretized coordinate in the continuous system is given by this expression for the kth mode qk equal to 0 to L fxt phi kx dx. Now here fxt is written f sine omega naught t into delta x minus L by t. This delta is the direct delta function which represents the discrete force that is acting at x is equal to L by 2. Now one property is there for direct delta function. If a function gx is multiplied by direct delta function and integrated between any limits, extreme condition is minus infinity to plus infinity, then we can get the value of the integral as the function evaluated at this point. So on this basis, this integral is evaluated. So evaluation of integral is given in this video and it is correct. So this is due to property of the direct delta function. Then regarding Hamilton integral equation, that is a time integral, but sometimes we carried out the double integration. How the double integration is coming? Because the Hamilton integral formulation is applicable for continuous as well as discrete system. But in continuous system, the energies, kinetic energies or potential energy have to be found by integrating this expression over the domain of the structure. So therefore, space integral also comes into picture. So therefore, double integration is necessary to find out this or to arrive at the equation of motion using Hamilton equation. Okay. Now, another question was asked, how to account for gravity in this case? That is, the case was a cantilever carrying a concentrated mass here. So concentrated mass is applied at the tip. So because of the presence of concentrated mass at the tip, boundary condition is not treated as free here. So therefore, the shear force is 0. That is the condition at the free end will not be valid here. Instead, the shear force at the free end should be balanced by the inertial reaction at the free end. That is the inertia force produced by the concentrated mass M. Now you can see that concentrated mass, when it produces the inertia force, that requires the acceleration. That is the second derivative of the this time function. So if this is the displacement of this beam, then the shear force is this and inertia force is this. So the third derivative now will be required to do with respect to x. So therefore, the third derivative of phi x, whereas the time function will remain as it is in the left hand side because it is a matter of partial derivative. Whereas in the right hand side, you can see that space function will remain as it is and time function will be differentiated with respect to time 2 times. So therefore, the omega square also appears in this right hand side. So that aspect was illustrated here and also replied in email. Then another question was there that regarding the this one problem was given for the axial vibration of bar due to some initial condition, and I have considered say first 5 modes. So in that case, some sign mistake was there, plus minus etc. That was detected and it was replied. So my intention was that if we consider more number of modes, you will see that the as you increase the number of modes, the magnitude of the displacement decreases. So that is what is reflected in the problem. The sign you can correct it, but main philosophy behind the problem is that the magnitude of the response decreases as the mode number increases. So that was reflected in the answers of the problem. So thank you very much.